All right, so again, welcome everyone. This is the My Field for Dummies webinar series put on by GBAT.net. And this features all sorts of different topics ranging about bat research and the work that we do as bat researchers on a very broad basis. And so I'm incredibly happy to introduce our speaker today, Hannah Wilson, who is a master's student at the University of Regina in Saskatchewan, Canada. And she is going to be talking about echolocation, acoustics, and pitfalls and everything. She'll go through everything with you and has put together an incredible presentation for us today. So with that, I'm going to go ahead and pass it off to Hannah, and she will be going through our topic for today. So enjoy.
Awesome. Thank you so much, Dana. Let me just actually practice sharing my screen, which I haven't done in a while. All right. Cool. Can everybody see? I'm going to go ahead and assume yes, since nobody's saying anything. So as Dana said, my name is Hannah Wilson. I'm a master's student at the University of Regina, where my project is about how bats react to different acoustic stimuli. So basically, how do they react to different sounds? But today I'm going to be talking to you about acoustic detection in general and echolocation in general, and what I think works and what doesn't. If you don't understand any of the words that are in the title, don't worry about it. We will go over what acoustic detection is. We will go over what echolocation is. But today we're basically going to be talking about in what ways do bats use sound, how researchers study that, how they study acoustics, and then a little bit of a practical intro of what you would need if you wanted to study sound. But before we do any of that, very briefly, if this works, there we go. What's the point of using sound? So in my opinion, I think the main reason why anything evolved to use sound is because of information gathering. So essentially what that means is animals are using sound to determine what is going on in their environment and using that to then make decisions about where they're going to go, who they're going to mate with, who they're going to avoid, and how to deal with what's going on in their environment. And then they're also making sound to figure out what's up. So for humans, that's something like asking a question. For bats, that's using something like echolocation to orient themselves in the environment. And then bats also use sound as a form of information sharing. So they're telling other bats and potentially other animals about what's going on in the world around them. And they're using and that's like a very, very brief, very basic intro of why we can use sound. I think that's a whole other topic. I think the whole idea of information. But when we think about bats in particular, we tend to think of bats using sound in two ways. We kind of think of echolocation as one box, and then all other forms of communication as everything else, which of course, like in reality, isn't how it works. There's a lot of overlap. Both communication and echolocation can both be ultrasonic. There's also an overlap between what different bats are using for information gathering. But technically, when we think of echolocation, we tend to think of it as orientation and for feeding, and then we think of other communication as pretty much everything else. So that's territorial calls, identification calls, mating calls, etc. And one thing that's important is not all bats echolocate, but we're not going to be talking about those bats because they're not cool. We're talking about only the echolocating bats. And also, very briefly, before we talk about echolocation, I wanted to talk about the history of echolocation because it's really, really cool, in my opinion. So echolocation is pretty new. We didn't actually coin the term echolocation until 1944, and bats were the first animals to coin the term echolocation. Before that, there was an 18th century Italian scientist, Spallanzani, who was the first person to realize or to write down that bats weren't using their eyes to see to avoid obstacles, but he wasn't sure, he didn't know it was because of hearing. He thought it was air movement, air pressure along the wings that was allowing them to navigate. And then it wasn't until the late 18th century that there was a Swiss naturalist who thought that it was because of hearing. And then it wasn't even until the early 20th century that people thought bats were also making sound in order to hear sound, but they couldn't figure out why that was happening. And so it was these two guys, Donald Griffin and Robert Galambos, who discovered echolocation in bats and discovered how bats use it. I'm going to be mostly talking about Donald Griffin because I know more about him, but both of them are super interesting figures who have done a ton of really cool ecological work. Wikipedia is frankly an excellent resource if you're looking for more information about either of them. But Donald Griffin was kind of the driver of the discovery of echolocation because he first got interested in it as an undergrad at Harvard and was working with a physics professor called Pierce to figure out what was going on. But it wasn't until he started working with Galambos years later where he figured out that bats were using echolocation to orient themselves. And frankly, I don't think their first experiments were what we would consider ethical, but some of the less horrifying ones is they used to tie the jaws of bats to stop them from making sound and then send them into their lab space to figure out if they could orient themselves. And then they would write down the number of times and figure out the percentage of times bats were slamming into obstacles. And what I think is cool is sometimes sometimes they tied the bats' mouths wrong. And so the bats were still able to make little bits of sound. And so their ability to orient themselves in the lab space would get better over time. And so that's how part of the reason they figured out that bats were using sound they produced in order to orient themselves. They also used to put balls of warm wax in the bats' ears in order to figure out if they were hearing. And then they used to use blindfolds to tie the bats' eyes shut to see if they were able to orient themselves. And then they used that to figure out that bats were making sound and then listening for the echoes to orient themselves, which is very cool. Later, Griffin also became a pioneer of cognitive ethology, which is basically the idea that animals have a consciousness and an intention in what they do. And I can't imagine doing some of the experiments he did and then later thinking that animals could potentially have consciousness and intention. Like that for me would be a little horrifying, but he was a very cool scientist. And he also, if you're interested more in the history of echolocation or what they knew about echolocation up to about the 50s, he wrote this very cool book called Listening in the Dark, which is very accessible to non-scientists because it was a series of lectures that he gave that he eventually transferred into a book. So I would absolutely recommend reading that book if you're interested in echolocation at all. It's a very good primer. But enough about the history. How does echolocation actually work? So the way that it works is that you produce a sound. That sound will echo off an object. So right now I'm talking at the computer and echoes are coming off my computer. And the echo will give information about what the object size is and what the shape is. It will also give me information about how far away an object is. So echolocation is also affected by things like clutter, so how many objects are in an area, because if you're producing sound and getting information from a whole bunch of different spaces, it makes it harder to detect what's going on and get accurate information. Different mediums also cause echolocation to work differently. So the way that sound travels through water versus air, it is very different. And so that also affects echoes and also affects the way sound travels. And then also sound clutter. So if you're in a city, you're getting a lot of different sound stimuli compared to when you're in the countryside. So bats have to deal with all of that when they're echolocating. And when we think of bats echolocating, we tend to think of echolocation as a way bats find their prey. So bats are clicking continuously when they're echolocating. The reason they're doing that is because they're moving in the space. So every time they echolocate, every time they produce a sound, they have new information on what's coming closer to them, what's appearing next to them is closer, but also their prey is also moving. So it's important that they continually echolocate whenever they're flying so they can figure out what's around them and also so they can figure out where their prey is. And although we can't hear it, bats' echolocation it's very loud. It's up to basically the sound of a fire alarm call. And we can't hear it because it's all ultrasonic, but the bats are basically screaming whenever they're in the air, with some exceptions that we'll talk about later. But the reason that bats produce an ultrasonic call isn't just to avoid us, but it's because the higher frequency a call is, it gives an animal, it produces a better detectability. So you can see more of what's in the area, or a bat can see more of what's in the area. And it also gives a better resolution of the echo. So you can also see more details about what's in the echo. So when a bat is calling out high frequency, what it's doing is saying, okay, now this way I can get more information and I can get better information of the echoes that are coming back to me. But another reason they have to call continuously is because the higher you call, the less far it travels. And you can see that with the way that a train honks. Train honks are really low because it travels farther in space. Bat calls being really high don't travel very far in space. So bats are also continuously calling because they need to, because the sound is not going very far. So they're only getting information within a pretty short distance of themselves. The other reason they developed ultrasonic echolocation is potentially because many of their insect prey and also some of their predators can't hear high frequencies. So there's an evolutionary advantage to calling super high frequency, because then prey doesn't know they're coming and predators cannot attack them. Well, they can, but it
Yeah,
makes it
just
harder. And then, of course, different species will develop different techniques of echolocation depending on where they are, what their prey is, and what's going on. So for me, I live in Canada, and three of the species that are most common where I live are the little brown bat, the hoary bat, and the silver-haired bat. So the little brown bat is the call that's on top. This hoary bat is the call in the middle. Silver-haired bat is the call at the bottom. And where I live, the hoary bat and the silver-haired bat are presumed to have pretty similar prey items, and the little brown bat is presumed to have smaller prey items. And so you can see when they're calling at different frequencies. The reason they're doing that is because the little brown bat calls they're looking for much smaller prey than the hoary bat or the silver-haired bat. And so if they call at a higher frequency, they're getting that better detectability, so they can see more and they can see higher resolution, which means they can see smaller items. But this is a pretty typical, these calls are pretty typical of Vesper bats. They're still relatively loud for a bat call, and then bats in different areas with different prey items and different specialities will have different calls. So one of the bats I think is really cool are whispering bats. So whispering bats, I think, are so awesome. First of all, they're adorable and they have giant big ears, which I love. But whispering bats, their prey is typically something called eared moth, and these are moths that have basically evolved so they can hear echolocation pulses. What that means is that when a bat is calling, the moth will hear it and it's like basically fold up and drop to the forest floor or whatever floor is in front of them. The idea of doing that is so bats will lose them in the echolocation space and they'll drop out and the moths can survive. So whispering bats have developed something really cool, which is they whisper. So instead of shouting big echolocation calls, they make really quiet calls that only see about 3 to 5 meters ahead of them. And they don't use their echolocation to capture prey. They're using it to navigate. And they're using their giant ears to hear wing flutters and hear sounds of insects moving. And they use that instead to capture their moths so they can get really quiet when they get close. But the point of using echolocation at all is basically so they can still navigate and figure out what's around them without alerting any of their prey nearby. Kind of on the opposite side of the spectrum are fishing bats. So fishing bats, as their name suggests, catch fish. And there are about 6, I believe, out of the nearly 1,500 species of bats in the world are fishing bats. Part of the reason there are so few bats is because, as I mentioned earlier, sound travels really differently through air and through water. And so bats that are fishing bats can't actually detect fish underwater. So it makes it more difficult for them to figure out how to eat them. But these bats have managed somehow. So the most famous example of a fishing bat is the bulldog bat, which is pictured in this image. And they're super cool because they figured out how to not only recognize when there are ripples in the water, and so they use echolocation to recognize ripples in the water and realize when a fish is there. But bulldog bats also can recognize specific fish echoes versus insect echoes, and they use that to determine what their prey is and whether or not to attack. Other species of fishing bats also use ripples along the surface of the water to figure out if there's food nearby, but they don't seem to be able to differentiate between fish and between insects. But that's okay because these guys will eat insects too. But they are so freaking cool. I think that's pretty amazing. But of course, not all bats eat meat and eat insects. And so nectivorous bats will also use echolocation to find flowers. So for example, a good example is on the left, this is something called a mucuna vine. And then on the right, this is a nectivorous bat, a glossophaga. And they seem to have co-evolved to have made it easier to find nectar. So the mucuna vine has 3 major types of flower. They have flower buds, which haven't fully blossomed yet. They have virgin flowers, which are basically flowers that haven't had any bat pollinate them yet. And then there are exploded flowers, which means that bats have been there, they've had the nectar, and the flowers have been pollinated. What's really interesting about these flowers is that the virgin flowers will produce a whole bunch of nectar for the bat, for any first bat that shows up. And then with the exploded flowers, they will produce significantly less nectar. So bats will preferentially choose virgin flowers over exploded flowers so they can get as much nectar as possible. And in echolocation, buds, virgin flowers, and exploded flowers all sound different. And so bats can preferentially choose virgin flowers because they can hear the difference between in the shape of the flowers in the echolocation space, which is unbelievably cool. I think that's really awesome. But my project and what I'm more interested in is not echolocation, but in communication, other forms of communication. And I think in the future, that's probably what a lot of research is going to end up focusing on. So when we talk about communication, we're talking about things like distress calls. And so a distress call is essentially a scream that an animal will make when it's afraid or when it's in danger. So typically when we think of distress calls, animals will use them to startle predators. So the idea is if you scream in somebody's face, they're going to let you go. You can warn your relatives around you that there's danger here, don't show up. Or you can try to attract attention to yourself. So your relatives will come find you and fight off whatever is attacking you. Responses to distress calls can include like running away. It can be to attack whatever is attacking the caller. Bats can investigate and figure out what's happening in the area, or they can do nothing. And distress calls are super different from echolocation calls because the point of distress calls is to be as loud and as disruptive as possible. So I want to show you 3 different call types. We have the little brown bat at the top again, hoary bat in the middle, and the silver-haired bat at the bottom. Except instead of echolocation calls, these are distress calls. And so you can see that all 3 calls are a lot lower. So the red line on this graph is what is at the human hearing range. And little brown bats in particular, when they're echolocating, are way higher than the human hearing range. And all 3 bats are much louder. They're much less structured calls, and they're very broadband. So the idea is that like animals across the hearing spectrum can hear these calls, and they're traveling way farther. So a lot more things can hear this distress call. The point of doing that is so these animals can react and scare their predators. So you can already see that the call structures are super different between echolocation calls and other forms of communication. Other ways that bats can use other different types of non-echolocation calls are for individual identification. So there are bat roosts with tens of thousands of bats in them. How are mothers supposed to identify their babies? Well, there's evidence that bats can use individual ID. So mothers and babies have specific voices the same way that humans do, and bats can recognize that voice and use it to find their baby or their mother. And then also there's mating. So I love this. So hammerhead bats, which are the really weird looking bat on the right, have been observed to do something called lekking. And so what lekking is when 2 or more males will gather in a specific location without a noticeable food or habitat benefit and basically attract females using the power of performance. So you see this with birds a lot. So turkeys will do it and sage grouse will do it, where they will dance and they'll sing. And there's evidence that hammerhead bats are at least singing to attract females, which is very, very cool. And then on the left, that's a common pipistrelle bat. And there's evidence that they have started to do the same thing, which is awesome. So these are just some of the ways that bats are using sound in nature. And the reason that we know any and all of this is because of the study of bioacoustics. So what is bioacoustics? Bioacoustics is the study of how animals produce, transmit, and then receive calls. So when we say for bats, when we're saying production of a call, bioacoustically, what we mean is we're asking, how do bats make sound? So we're looking at bat anatomy and we're looking at their neurophysiology. So what's the shape of their tongue? What is the size of their larynx? How are they doing it? What neurological transmitters are helping them produce an ultrasonic sound or any sound? When we're talking about transmission of sound, we're asking how does sound travel through a certain medium? So air, water, like solid. And then when we're talking about reception, what we mean is how are bats hearing sound and how are they responding and receiving the sound? So when we're doing that, we're talking about things like ear shape, like as you can see, it's very obvious in the far right bat here. But you're also talking about cognition and neuroscience. When we think about bioacoustics, what we're also thinking about is the evolution of acoustics. Why did bats or why did any animal evolve to hear specific sounds or produce specific sounds? And that's, I think, where ecology comes into play, because behavior is an indicator of why a specific behavior evolved. So, for example, when we talk about mating, bats evolved to produce mating calls because for some reason females find it attractive, or bats evolved to use ultrasonic sound when they're echolocating because it helps them avoid predators and it helps them get better resolution of the area around them. So we talk about bioacoustics, that are some of the questions we are asking. But in order to answer a lot of bioacoustic questions, that's when we need acoustic detection. So when I talk about acoustic detection, generally what I'm talking about is detection using detectors, transmitters. So an acoustic detection in general means looking, hearing sound. And we do that using acoustic detectors, which are equipment that we'll go into that is specified to hear sound around the environment. And typically when we use acoustic detection today, we're not doing invasive, or we're not doing specifically experimental projects. We tend to use it passively. We use it in research to figure out what bats are in an area, what species they are, how many they are, what areas they're using. And also a lot of industry is using it. So a lot of consulting firms, if they're trying to do an environmental assessment to figure out what bats are in an area, will use acoustic detectors. The reason that they're doing that is because acoustic detectors are much more passive than other ways of trying to figure out if bats are in an area, such as netting, which is basically when you put up a giant net over a certain area, bats fly into it, and then you can literally count how many bats you catch in a night. The reason that you would use acoustic detectors instead is because they're passive. So instead of having a giant net and having bats fly into them and taking half an hour to hold the bat, measure the bat, figure out what it is, and then letting it go and giving it a lot of stress, instead you could just put an acoustic detector up and find the same number of bats the same way. Long term, it also means that it's cheaper. It's cheaper to just buy an acoustic detector and then leave it up, then use human labor to do bat work. And then you can also leave acoustic detectors out for a long period of time. You can leave them for, depending on how much battery you have, for a few weeks. There are also pitfalls for acoustic detectors, which I'm about to go into. But spoiler alert, I think acoustic detectors are great, love them. I don't think they can be used for everything. But what is an acoustic detector? This picture is an example of a mini acoustic detector. And so this detector can do pretty much everything a regular acoustic detector can do. But you basically turn it on, pair it to your phone, and then there's an app on your phone where you can control everything. And so there are regular acoustic detectors, and there are mini acoustic detectors, which are what I would use during my project. You can also have acoustic detectors that don't detect ultrasonic sound, which are significantly cheaper than the ones that don't ultrasonic detectors, and they are used often in bird research. And then detectors can also have different microphones. So you can use whatever microphone is on the detector. You can also separately buy an acoustic microphone that can go a farther distance, or would theoretically also give you a better sound quality. What all detectors do is that they'll detect sound across a time that the researcher or the user of the detector has specified. And the calls they record will depend on the frequency specified by the user. So all these detectors, you can say, I only want calls that are above or below a certain frequency. So if you're trying to detect bats and you don't want to get a bunch of birds in there, then you can make it so only sound above, let's say 20 kilohertz, which is super high, will be detected. And then you can also specify the volume of what you want detected. So only calls above a certain number of decibels will be detected. And that way you can avoid just getting random trees in the background, or if somebody claps their hand really, really quietly, you can avoid that. The issue there is that you can risk missing things like whispering bats, which are calling very quietly, if you set your volume settings for too high. And then you can also set the number of calls that you need to hear before you count it in your detector. So the idea is that if you hear at least 3 calls made at a time, then you know for sure it's a bat there and not just a random sound. And you can use that also to reduce the amount of detections that you're getting and like reduce the chance that you're not just going to be getting a whole bunch of different sounds and just not just bat calls. However, I mentioned that there are pitfalls to using acoustic detectors. There are many. I still love them very much, would use them all over again. But 2 major pitfalls is for me in particular, since I live in Canada, are battery and winter. So battery on these guys is it's a pain. It's using any technology, using batteries is a pain. And for me, in the winter time, battery runs out really fast. So you can only leave them out there for a certain amount of time. Uh, and even if that is a few days, it's still a pain to go back to your certain site every few days and just replace the battery. Um, Acoustic detectors can also be affected by human error because you do have to program them yourself. So if you don't have very much experience, or if you didn't read the manual, or just like pressed a button slightly wrong, then you can mess up what your acoustic detector is hearing. And then acoustic detectors are like a lot of money up front. They're at least $200, which in the scheme of research isn't that bad. But for me, as a poor broke grad student, seems like a lot. And then if you're in anywhere, you also have to you do have to worry about these guys getting stolen. A lot of the time it's not malicious. People aren't stealing them just because they don't want you to do your research. People think that, I mean, they may not know what it is, or they may think it's something to do with poaching. So for myself, when I was using detectors, the first year I used these full regular size detectors, and I had a microphone, which was a pain. It sucked because setting up the microphone was really long and I had to worry about it not getting tangled. I was terrified of ruining everything. The next year I used a mini acoustic detector, which were great, absolutely would recommend them, except that for whatever reason, one of them had a really horrible battery problem. So it would run out of battery in 2 hours. I had no idea what was wrong. It took me a few days to realize what was going on. By the time I realized, I had lost 3 days of data. So if any of you are planning to use acoustic detectors in the future, then keep in mind that they can be a problem. And you just make sure you're testing constantly is all I can say. But what we're doing is we're using the acoustic detectors to record calls. But in order to actually figure out what the calls are of and what they're saying, you have to use an analysis software. So on the screen, this is a photo of a bat call of calls I found in analysis software called Kaleidoscope. And what this will do is put the call on a screen in front of you, and you can use that to identify the bat that's calling, or the bats plural that are calling, the species they are, how many they are. And a lot of analysis software now has something called auto ID, where it will automatically identify whatever species is calling for you. There are several problems with auto ID. The number one thing is that they're only going to automatically identify one species. So for example, in this picture on the screen, there are at least 2 species of bats in this photo. If I were to use auto ID for this software, then it would only identify one, which is a problem. Another issue with auto ID is that between continents, auto ID is using acoustic libraries to identify your calls, and between different continents and between different countries, the acoustic libraries are not even. So if you're in North America, the options you have for auto ID are a lot greater than if you're in Southeast Asia. So that's also an issue. There's also been quite a bit of debate about, frankly, whether or not we should use auto ID at all. When it first became popular, or when you first started being able to use it in software, the debate was that you should only use auto ID to identify calls. You shouldn't be manually vetting calls at all, because then you're introducing human error into a call. But now it's kind of gone the other direction, and now people are saying you have to manually vet every single one of your calls. And at that point, what's the point of using auto ID whatsoever? I think right now, at least in my lab, the plan is we're vetting like 10 to 50% of the calls that we use during auto ID. But it is totally different. And the other issue is that different analysis softwares will auto ID bats differently. So I think there's like something like a 30% agreement between an analysis software like Kaleidoscope versus another popular software called Sonobat. So that's a problem. I think long term, we should probably just manually vet all our calls, even though it's kind of a pain. And if you want experience at all, you should be able to manually ID a call. So let's learn how to do that. So if you were using an analysis software and you wanted to manually ID a bat, the first thing you would want to do is learn the geography of where you were getting your information from. So for my project, I set up my detectors in an area called Cypress Hills, which is in southwestern Saskatchewan in Canada. The only bats I really have to worry about there are the hoary bat on the top left, the red bat on the bottom left, the silver-haired bat in the middle, the little brown bat on the top right, and the big brown bat on the bottom. Those are the 5 common bats that I would get in my area. We're pretty much not going to get another bat. So when I'm trying to ID calls from the Cypress Hills, these are the only 5 species that I have to worry about. It is very different to be in somewhere like Honduras, where you have 70 to 80 species of bats in the same area. So a huge bummer for people who live in Honduras. But for us, and for my purposes, we really only have to worry about these 5 bats. And you can use that information because the reason geography is important is because if 2 different bat species have a very similar look and call, but one is from Singapore and the other one is from Vancouver, then you don't have to, then you can determine that it's not going to be the same bat species if you're only collecting calls from Singapore. The second thing that you would need to ID a bat call is to know the frequency at which bats call. When we talk about frequency, we typically mean the lowest frequencies bats can call at, and we also want to know a little bit the highest if we know the highest frequency bats call at, and then where the most power in the call is. So in this image, there are also at least 2 bats here. You can see one bat on the far left is calling, and most of its power and its lowest frequency is at about 40 kilohertz. So that's going to be completely different from the bat where most of its power and its lowest frequency is at 25 kilohertz, which is the bat on the far right. You can also see more easily on the bat on the far right that there seems to be 2 different colors or multiple different colors in the image. Some of the colors are kind of green and some of the colors are red. Red means that's more power in the call, so that's where they're shouting the loudest. And where that most power is in the call can also be used as an identifier for what bat is calling in the area. A third thing that you need to ID bat call is shape. So when you are using an analysis software, there are 2 main view screens you can look at. You can look at the call in regular time, which is what this is. This is all in regular time. Or you can look at a call in compressed time view. And what that does is basically just widen out the call. And there are some species that have very distinct shapes at certain frequency. So for example, the silver-haired bat has a very distinct flat call at exactly 25 kilohertz. And so only the silver-haired bat will really do that. That is how you can identify a silver-haired bat from a big brown bat or a hoary bat. So shape is also a good way to tell what species you're dealing with. The fourth thing that you need to figure out how to ID a bat call is the pattern of the call. So these are 2 examples. The top example is what I would call a steady call. So all the calls end at about this, have a similar lower frequency. They're all basically along the line. There's a little bit of difference, but not by a lot. And then the call at the bottom is a bouncy call. And so these are more typical of things like hoary bats and red bats, where the lower frequency bounces around the screen. And you can pretty obviously see the difference. And you will also see more of a difference once you get experience identifying bat calls. I sucked at identifying bat calls 2 years ago, and now I am better at it. I wouldn't say I'm incredible, but that's when you have people who have more experience around you, and there are lots of resources you can use online, and hopefully by contacting other people who know better than you how to identify bat calls. The reason that I wrote me before I knew I was getting into is because it is absolutely tedious to ID bat calls. It's really fun because it is like solving a puzzle, but after a while it can get tedious. So we're going to have a bit of a pop quiz, and we're going to practice IDing bat calls. If you would like to take a picture of this screen with your phone, then you can. If you can remember it, even better. But right now, we're going to try to ID a bat call between a hoary bat on the far left, an eastern red bat in the middle, and a little brown bat on the right. So I'm going to show you a screen with a specific bat call, and then in the chat, I want you to tell me what bat call it is. I will give you, let's say 30 seconds. If you think you know what bat it is, put it in the chat. If not, I'll tell you the answer, so don't worry about it. Awesome. Sweet. So I see in the chat a couple of people have gotten it. Yeah, it's a little brown bat. The reason you know that is because the lower frequency is at about 40 kilohertz, which is much higher than either of the other two bats that were the option here. You can see that it has a steady call. There's pretty much no bounce in the pattern. The shape is very steep, and geography doesn't matter. They're all in the same area. But if any of you were confused, that's because this was a little bit of an unfair question, because I included all three phases of a little brown bat call. There's the search phase, which is where the calls are very even and steady. There's the approach phase, and then there's the attack phase in a call. You can only use the search phase if you're trying to identify a bat call. That's because the approach phase and the feeding buzz phase, the feeding buzz and approach, where you can see it gets really steep all of a sudden at the far right of this call, get really weird. You cannot use them to identify a bat call because you can think they're totally different species. So if you're trying to ID a bat call, only use the search phase. This is also probably two bats in this. I'm sorry for using this as an example for you, but this is a pretty good example of a hoary bat call. Now that you know how to ID a bat call in general, you can use that to do species identification more broadly. But you might get messed up if two species have very, very similar looking calls. So for example, where I do my research, the silver-haired bat and the big brown bat have very, very similar calls. So it's almost impossible to actually separate the two. They both call at about 25 kilohertz, although the big brown bat can go lower and silver-haired bat never does. The shape is pretty similar most of the time, unless you get to that 25 kilohertz mark for the silver-haired bat. They have very similar patterns. They're not bouncy. And they have overlapping geography. So there are specific instances where you can separate the two. So for example, big brown bats will have calls that go even higher than 60 kilohertz versus silver-haired bats never will. So that's if you see a call that goes past 60 kilohertz and you know it's a big brown bat, or if you see a silver-haired bat call that's completely horizontal at exactly 25 kilohertz, and you can probably guess it's a silver-haired bat. But other than that, you pretty much just have to give your best guess. And in my opinion, it's always best to go more conservative with your bat calls. So if I saw this, I would say silver-haired or big brown bat. So the solution, if you're trying to figure out which of these two species are in the area, or if both species are in an area, is to do netting. So you do have to set up nets and just catch bats and see what you get. And I think species ID using acoustic detection is great for presence absence if you know exactly what species are in the area. But if you're confused at all, then I do think doing netting is super important. And now that you're all species identification experts, we can do some other studies. So we can also do species abundance studies. Using acoustics to do species abundance, I have some issues with. Happy to be convinced otherwise if any of you have strong feelings pro using acoustics for species abundance. But when we talk about the abundance of a species in the area, basically what we're trying to figure out is how many bats are in the area. And when you do that with netting, essentially you're setting up a giant net, waiting for bats to fall in and counting how many you get. When you do that using acoustics, what you're doing is you're trying to figure out how many times you hear a bat. So how many times a bat passes by your acoustic detector. You're trying to figure out the number of passes that go by within a specific time period. And then for you to get an abundance study, you need to have a comparison. If you're just setting out an acoustic detector and letting bats fly by, then you're not getting it, you can't compare it to anything. So it's not an effective comparison, which means you're not really doing a species abundance study. The other issue is that if you don't have any comparison, it could just be the same bat flying by your acoustic detector a whole bunch of different times. And so you're not actually getting more than one bat in the area. I think for species abundance, when you're first getting to an area, you really need to do netting. Where I think abundance studies can be interesting is when you have an effective comparison in the same area at the same time, and you can compare compare two different sites at the same time, and then compare. Okay, this detector got way more calls than the other detector, and so that tells me this site probably has more bats than the other site. But you always need a comparison when you're doing like an abundance study. So I think site selection studies with acoustic detectors are really cool because essentially what you're doing is you're doing an abundance study, but at different sites. So you can set up 3 acoustic detectors. You can set it up at a forest edge, so where the forest meets the grass here. You can set it inside the forest. You can set it up out in the open space, and then you can compare the frequency that you hear bat calls inside the forest at the edge of a forest in the open space. And then you can have an effective comparison and compare the abundance between different sites. The issue with setting up nets in open areas, as well as setting up acoustics in open areas, is that the bats need to be getting close, really, really close to the acoustic detector for the detector to pick them up. So if you set up a detector in an open area and you're seeing way fewer bat calls in your open area, it might be that the bats are still there, but they're just flying too high or too far away from your detector to be picked up. So when you're choosing a site and choosing where to place your detector, it's important that you have kind of a tunnel, or you take into account that maybe you're not going to catch every single bat that's flying by. Where I think acoustic detectors can be really cool and useful are in urban studies. The reason for that is that setting up a giant net in the middle of a downtown street is super invasive, and people are going to yell at you, as they should. So I couldn't set up a mist net to catch bats in the meatpacking district in New York. Instead, you can put acoustic detectors up there and hopefully try to catch bat sounds. It's way less invasive than setting up nets. You can set up acoustic detectors at many different places at a time, and you can get to places that nets don't make a ton of sense. Issues are you have to worry about sound clutter. Urban areas are way louder than rural areas, and you do kind of have to worry about things getting stolen. But I think we give city dwellers a bad rep sometimes. Another study you can do is about timing. So you can place an acoustic detector at the same site and then set it for a super long period of time. You can do daytime, nighttime, or dawn through dusk, or dusk through dawn, figure out when bats are most active. You can do it throughout the year and figure out if there's a difference in timing. And that way you can figure out when bats are flying the most often. I think the main issue with acoustic detectors is that setting up detectors is hard. We've already talked about human interference, but there's also animal interference. There are also a ton of things with acoustic detectors that can result in bad detections that you don't have to worry about if you're just setting up a net. Like if you get ripples in the water, or if you have a large bank, then it can cause a lot of sound distortion, which can make it seem like you have more bats in the area or fewer bats in the area than you do, or you can't identify the species. Wind is a huge issue because wind is super loud and it can completely mask the sound of a bat call. And then the other thing you have to worry about with the acoustic detectors that you kind of have to worry about with anything is finding a tunnel where bats will actually pass through. So you can't use just detectors for every study, but also not every study involves just setting up a detector and leaving. You can be a little bit more precise. And for doing that, you use a surprise ultrasonic speaker. And ultrasonic speakers are basically speakers that play ultrasonic sound, so a sound that's higher than the human range of hearing. The main issue with these speakers is that they're insanely expensive, and then some of them have a very small frequency range. So you can't use them for everything, and they might not be reasonable to use for everything. But if you have speakers, you could do much more experimental studies, by which I mean that you can play back different sounds from nearby predators. You can play back sounds from prey. So if your bat catches lots of moths, you can play back moth sounds using an ultrasonic speaker and see if more bats show up. Or you can play back different bat sounds. So this summer I played back bat feeding buzzes from different species and tried to figure out if bats showed up more when I was playing feeding buzzes versus when I didn't. And then I also did a lot with distress calls. So for my experiment, what I did is I recorded bat distress calls using an acoustic detector and then played back those distress calls using an ultrasonic speaker. Originally, when I came up with the experiment, I did not realize that bat distress calls were ultrasonic. And so I thought I was going to be super clever and use just a Bose pool speaker to do my experiment. Turned out that didn't work, so I had to buy this uber expensive ultrasonic speaker. And using that, I could play back distress calls from different species of bat to figure out how other bats in the area reacted, if they were running away, if they were approaching, if they cared at all about what was going on around them. And when you do that, you can come up with a bunch more interesting experiments and interesting reasons, or interesting questions when you're doing playback experiments, when you're not just passively listening to it for an acoustic detector. You can actually add in your own manipulation. But overall, for acoustic detection in bat, I think acoustic detectors are wonderful in many ways. I think they can be used for species ID. You can do a lot of experimental work with them. I think it's great that you can use them cheaply and you can use them effectively. I don't think they are worth it for every single study you do. I suspect that playback experiments and specifically work on social communication is going to become a lot more common in the future, especially as these things hopefully get less expensive. But acoustic detectors and playback experiments are not a substitution for netting. If you're deciding which one to do, ideally do both. If you can't do both, then you really need to think hard about what would work most effectively for your project. And because acoustic detectors are passive, there are problems with detectors that you're not going to find out until after the experiment and all your funding is gone. So that can be a problem. But it doesn't take away from the fact that detectors are really cool. Bat sounds are cool as hell. And they're really effective in conjunction with other forms of research. I think if there's one thing that I want you to remember from this presentation is that there's not going to be ever going to be one form of technology that solves all your problems with research or solves all your problems with, well, frankly, anything. But it's our job as scientists and it's our job as people who use technology on a day-to-day basis to figure out where those limits are and find those solutions as they appear. So with that, thank you very much for listening to my presentation. And if you have any questions, please feel free to put it in the chat. I will do my best to answer. And if not, thank you so much for coming early in the morning, and I appreciate you showing up on a Wednesday. Thanks.
Thank you so much, Hannah. We did have a couple of questions that came through the chat as you were talking. First, we have a question from Quincy. If I'm using multiple detectors, how far apart should they be? How far apart should they be deployed or set up?
Okay, so a great question. Worst possible answer is it really depends on your experiment. If you're doing a site selection experiment, then you need to set them up pretty far apart. When I was doing my experiment, I believe I have a picture in one of these. I set up my acoustic detectors really close to each other. Okay, here you go. The picture on the left, you can see I have my speaker in the middle, and then there was an acoustic detector like a meter away from the speaker, and then another one that was 3 meters behind the speaker. For me, I was trying to capture bats that were all in the same area, so I set them up really close to each other, but it really does depend on what your project is.
I would agree with that. It very much depends on the project. We have a question from Varsha. They say, I guess handheld or release calls might be different than when a bat is free flying. So how do we sample calls for reference of captured bats?
Ooh, so when I was collecting calls, I needed to collect distress calls and just regular search phase calls. So the way that I did that is I just set up an acoustic for the just regular echolocation calls. I set up an acoustic detector, let the bats go by, and then at the end, the detector is recording every single call you get. So you will have some good echolocation calls that you can use as a reference. And then if you have a bat in hand, they are still making sound. I don't think you can use them for echolocation calls. If you mean captured bats, as in bats that you have captive in a certain area, they're still going to be echolocating. If you want to get a good reference call, what I would probably do, and Dana or Susan, if you have better ideas, please feel free. I'd probably leave one bat in a captive area, put an acoustic detector in there, and then just let it fly. And it's still going to be making echolocation calls. And that way you can make sure you're only getting the one bat. That would be my.
Yeah, I was going to say something like if you want to make sure that you're just capturing echolocation calls or foraging calls, then something like a flight cage would work well. But yeah, they're going to be behaving differently if you just release them from hand. That call is going to be likely different.
Yeah.
We have another question from Quincy. How should I go about creating a release call library?
An excellent question, Quincy. I would also love to figure that out. For myself, what I did is I basically had a bunch of calls, labeled them, and I use them for my own reference. If you're looking for an actual release call library, there are specific people and specific organizations that you can talk to. Again, Dana and Susan probably know a lot more about them than I would. But if you're just creating one from your own reference and you have a bunch of different back calls, I would just make sure they're labeled to the best of your ability and set them up by species and by site.
Yeah, I feel like if you're doing a release call specifically, then you're probably going to potentially have to just hand release and record
Yeah.
to get those types of calls. There are resources such as, at least for North America, there's NABAT, which has a huge acoustic library. And Bat Amp also has a huge acoustic library, but that's more focused on North America. So very much depending on where you are. The reference library is different.
I'm also not sure if they have specifically release calls.
Yeah, that might be something pretty specific for a project. So
yeah.
I'm just going to quickly interject. There probably are not that many that have just release calls, but if you would like to learn more about how to make your own call library, we have not only Chirobox, which is linked on the GBATnet website, but also there are materials available through one of our member networks, BCI, where they will give you guidelines about how to do a lot of that, taking calls and everything like that. And if you are new to it, you can check that out as a way to start.
Excellent. Thank you, Susan.
Yeah.
Do we have any more questions for Hannah? Okay. Well, I guess that kind of wraps up this first session back for our webinar series, and we are going to continue having these again every month. It's most likely going to be the first Wednesday of the month, same time, same place. So I hope to see a lot of you back, and thank you all for joining us today. And let's give a big thank you to Hannah. So thank you, Hannah, so much for giving our talk today. It was an incredible presentation. So thank you so much.
Thank you, Dana, and thank you, Susan, for having me.
All right. Thanks, everyone. Have a great day.